Hello, friends. It's a beautiful evening wherever I am. I hope you are doing great. And today I would like to take this opportunity to record solved past paper questions of electric fields. Note that these solved past paper questions are going to be at least in three parts, if not four. But the first part and maybe the second part will only involve the simplest concepts of electric fields, and most especially in a uniform electric field. So please, I hope you will enjoy this, but before you watch this video any further, make sure you have subscribed, share the video, like, leave a comment, and also at the end of this video, before you watch the video, I have attached a copy of a past paper document that you can download, print, and when you are watching the lessons or the videos, you can always work through as you follow with the video. I will attach the document. I will attach the link to the document at the end of the video. So do not forget to download the document. It is in PDF. Or you just when you click on the link, I'll get a notification to share the document because it is big. It is in Google Drive, and then you will print. And then as you are watching the lessons, as you are watching the past paper questions being solved, you are also following through. In fact, you can even pause the video. You try to first work out maybe in a pencil, and you can now mark yourself while following the solution from the video. Thank you, and I hope you are going to enjoy this. So let us find our document. Let us find our document. I hope you have already downloaded your document. This is the document I'm talking about. It is Master Key to A-Level Physics, and that is Physics 9702 Revision Questions, Paper 4. This is a try edition for 2022 by Ivan Brian Mulumba, that is IBM. Those are some of the contacts you can always contact. And so that is how it looks like. And when you scroll down to the second page, you'll see the table of contents. And so today we are looking at electric fields. We are somewhere here at electric fields. So let me try to select a pen since we normally use blue. I'll reduce the thickness. So we are here on electric fields. So I'm going to look for page 62. Page 62. Page 62. Okay, so it seems my typing has not responded. I'll just scroll down. I'll just scroll down to page 62. Okay, so here we are, 62, page 62. This is unit 2, and that is electric fields. Remember, unit 1 was actually gravitation, so we can now proceed from this point. It's raining, and I don't know if it will be very clear, but I will try my level best to be loud and clear. Okay, let's start. The first question is telling us to define electric field strength. So from what we have studied so far, we now know that electric field strength is the force acting on a unit positive charge. I've always been emphasizing that we imagine a unit positive charge in an electric field. Therefore, electric field strength is going to be defined as the force per unit positive charge. So we define electric field strength as the force acting on a unit positive charge. So simply electric field strength is the force per unit positive charge. Part B, two very small metal spheres X and Y are connected by an insulating rod of length 72 millimeters. A side view of this arrangement is the one which has been shown in the diagram which you see on your screen. There is a uniform electric field which is upwards and its value has been given as that one. The charge here is negative 3e and the charge here is 3e. We know that E is the elementary charge which is 1.6 times 10 power negative 19 coulombs. That is E. Sphere X has a charge of that, sphere Y has a charge of that, where E is the elementary charge. The rod is held at its midpoint Z at an angle theta to the horizontal. The rod and the spheres have negligible mass and are in uniform electric field. The electric field strength is 5.0 times 10 power 4 volts per meter. The direction of the field is vertically upwards as shown with that arrow. The electric field is produced by applying a potential difference of 4.0 kilovolts between two charged parallel metal plates. Calculate the separation between the plates. Remember, we have already defined electric field strength E as the force acting on a unit positive charge, but also we earlier on established that electric field strength is equal to V over D. So we want now to find the distance between the plates, which is small d. So from D equals to making D the subject, D is going to be V over E, where E is the PD between the plates. And they have given us the PD as 4 kilovolts. Therefore, I substitute this will be 4 times 10 power 3 divided by E, which E is 5.0 times 10 power 4. And when I press my calculator, so pressing the calculator, this is giving me a 8.0 times 10 power negative 2. Always it's good to write answers in this curriculum to not less than 2 significant figures unless they are exact or unless not required. But in most cases, answers are good enough to more than two significant figures, not just one. The second part of the question, describe the arrangement of the two plates. Include your answer a statement of the sign of the charge on each plate. So let's move back to the charges. The field is upwards. The field is upwards, and if the electric field is upwards, it means that by all means the plates must be horizontal. Because the field is upwards, by all means the plates must be horizontal. So I can assume or think of the plates as being horizontal because the field is upwards. Note that a uniform field is always perpendicular to the parallel plates. Since the field is upwards, then the plates will be in a horizontal plane. But then our task is to identify which plate is having a high potential or positive and which plate is at lower potential. Since field lines originate from high potential to low potential, we can predict that the bottom plate is going to be positive and the top plate will be negative because field lines originate from high potential to low potential. Therefore, in our explanation, even drawing on the diagram could be enough to give the examiner the idea that you know what you're dealing with. But if you want to put it in words, we can simply say the plates are horizontal or are in a horizontal plane. Plates are in a horizontal plane. Plates are in a horizontal plane above and below. and below the rod, as we have drawn on the diagram. But the top plate is negative, and the bottom plate positive. So that is the arrangement of the two plates. They are in a horizontal plane because the field is in the vertical plane. The field is always perpendicular to the plates. And they're in a horizontal plane above and below the rod, the top plate being negatively charged and the bottom plate being positive. That is how we would answer that question precisely. Determine the magnitude and direction of the force on sphere Y. The magnitude and direction of the force on sphere Y. The force, we know that the force due to the electric field is given by charge times electric field strength. The charge on sphere Y has been given as 3e from above. So this is going to be 3 times 1.6 times 10 power negative 19 times the electric field strength, which is given as 5.0 times 10 power 4. And when I press my calculator, from my calculator, I'm getting 2.4 times 10 power negative 4 in newtons. So that is the magnitude. So I get negative 14 newtons. That is the magnitude. Then sphere Y, we want to predict the direction. Let's check sphere Y. Sphere Y, the charge is negative and it is next to a positive plate. The force on the negative charged particle is in the opposite direction to the field, or to the direction of the electric field. The force on a negatively charged particle is in the opposite direction to the direction of the field. So the field, since the field is upwards, the force on the negatively charged particle is going to be downwards. So here we can say for the direction we can simply say it is vertically downwards. It's vertically downwards. Okay, next part of the question. The electric force acting on the two spheres form a couple. Remember from AS, a couple refers to two parallel forces whose lines of action will never meet and they are acting in opposite directions. These two forces are equal in magnitude. In opposite direction, parallel to each other. Their lines of action can never meet. So one force could be in that direction, another one could be in the opposite direction, that their lines of action can never meet. These constitute what we call a couple. So we want to find this couple acts on the rod with a torque, which is given by that. Remember, torque is the same as moment of a couple or moment of a force. So the moment of a couple is given as that. And remember, moment of a couple is the product of one of the forces constituting a couple and the perpendicular distance between the two forces. So we want to find the angle theta of the rod. The angle theta of the rod to the horizontal. So we know that torque is equal to the force, product of one of the forces, times the perpendicular distance between the two forces. So let's go back to the diagram. So we can take one of the forces. We have already found that this force is acting vertically downwards, but we want the perpendicular distance between the two forces. Of course, the other force will be acting vertically upwards. We may want the perpendicular distance between the two forces. I will change the ink so that I draw the lines of action of these forces. So that one acts along that plane, and this one acts along this plane. So we want the perpendicular distance between these two forces. So the easiest way to find this perpendicular distance could be taking the rod into the horizontal. What does that mean? We are going to find the horizontal component of any of these lengths. We are going to find the horizontal component of, say, this distance in the horizontal, of course, plus this distance in the horizontal, which is the same as simplifying this one and multiplying it by 2, or taking the whole of this distance and multiply by the component of that distance in the horizontal. So when I turn this to the horizontal, when I resolve the length of this conductor to the horizontal, it will give me 72 cos, because the angle is between the rod and the direction I want to resolve to, so that is automatically cos. So the perpendicular distance is going to be 72 millimeters cos of the angle theta. So that is the perpendicular distance between the two forces, that is one acting upwards and another acting downwards. So having noted that, so the torque, which is given as 6.2 times 10 power negative 16, is equal to the force, the force on one of uh, one of the forces, which we calculated as being 2.4 times 10 power negative 14, then times the perpendicular distance, which is 72, of course, was in millimeters, so I'll say times 10 power negative 3 to change it to meters, cos of theta. When I make theta the subject, of course, it means theta is going to be the cos inverse of 6.2 times 10 power negative 16 divided by 2.4 times 10 power negative 14, then times 72 times 10 power negative 3 millimeters. And when I press my calculator, pressing the calculator is giving me approximately 69 degrees as that angle. Next part of the question, I don't know whether it's part, but it's part. Two parallel metal plates in a vacuum are separated by 0.045, so that is the distance between the plates. A PDV is applied between the plates as shown. A proton is initially at rest on the surface of the positive plate. So initial velocity of this is 0. The proton in the uniform electric field takes a time. This is the time it takes to reach the negative plate. So that is the time between the plates. Show that the acceleration of the proton is 4.0 times 10 power 12 meters per second. We want to show the acceleration to be that. Okay, I think the easiest way is to use the equations of motion. Because this is a uniform electric field, the acceleration is going to be uniform. Therefore, the equations of motion can be applied here. So using S is equal to ut plus a half at squared. S equals to ut plus a half at squared. We shall simply say that initial velocity is 0. This distance is going to be 0.045. This will be equal to a half times the acceleration times 1.5 times 10 power negative 7. And when I make acceleration the subject, so this will be 2 times 0.045 divided by 1.5 times 10 power negative 7. And when I press my calculator, oh, by the way, this is squared, this one is squared. So when I press my calculator, so this is giving me my acceleration as 4.0 times 10 power 12 meters per second as required. Part 2, calculate the electric force on the proton. Calculate the electric force on the proton. So we know that by this point, we know that force is equal to charge times electric field strength. Or alternatively, this could be mass times acceleration. It is a proton. The mass of a proton is 1.6 times 10 power negative 27. So this will be 1.67 times 10 power negative 27. Then times the acceleration, which is 4.0 times 10 power 12. And when you press your calculator, so this gives me a 6, approximately 6.7 times 10 power negative 15 newtons. Many times you always realize that the force will always be small, but the acceleration will always be big. So the power of the force is always negative, the power of the acceleration is always positive. Part 3. Use your answer in Roman 2 to determine the electric field strength. By definition, we say the electric field strength is the force acting on a unit positive charge. So the force is now 6.7 or 6. I had got exactly 6.68 times 10 power negative 15. So this would be 6.68 times 10 power negative 15 divide by 1.6 times 10 power negative 19. So pressing the calculator has given me 4.2 times 10 power 4 newtons per coulomb as the electric field strength. Next, please remember to download the document. It becomes hard to follow if you don't have the hard copy. Print and download and print. That's how it will become easier for you to follow through. Part 2 is saying, you remember we are using the answer that we obtained in part 2, and that was force, which was 6.7 or 6.68 times 10 power negative 15. So to find the potential difference V between the plates, by definition of from electric field strength also we saw that E is also V over D, which when we substitute or we make V the subject, V will be equal to D times E, and this would give us D. D was 4 point, what was the value for D? D was 0.045. D is 0.045, and E is 4.2 times 10 power 4, or 4.1. Actually, my exact value here was 4.18 times 10 power 4, and I rounded off to 4.2. So, but I will still use 4.2. There is no problem with that. And when I press my calculator, so pressing the calculator is giving me 1.9 times 10 power 3 in volts. Part C. An alpha particle is now accelerated between two metal plates. Remember the other one was a proton. An alpha particle is now accelerated between the two metal plates in B by the electric field. Calculate the ratio of acceleration of alpha particle over acceleration of a proton. So we have already seen that the force is given by mass times the acceleration, which is going to be the same as the charge times the electric field strength. So acceleration is going to be charge times E over the mass. Note that E is going to be the same. So I'm looking for the ratio alpha over proton. So acceleration of the alpha particle divided by acceleration of the proton is going to be, the charge of the alpha particle is twice E, the electric field strength is the same, the mass of the alpha particle is 4U, divided by the acceleration of the proton. The charge of a proton is E. Electric field strength is still the same, and the mass of a proton is actually 1U. So if I simplify this, this will be, so the ratio is going to be equal to twice E times capital E over 4U times U over E times E. We get the reciprocal. So all these ones have cancelled, and I remain with the 2 over 4, which is 0.5. So the ratio we are looking for is going to be 0.5. The ratio there is going to be 0.5 because all these ones cancel out, U also cancels out. So that is our question. Next question, define the coulomb. We know that coulomb is a unit of charge, and charge is current times time. Note that we can define a unit in terms of other units. So if coulomb is I times T, then we can define a coulomb as ampere times second. So a coulomb is 1 ampere times second, 1 second, that is a coulomb. 1 ampere times 1 second, that is the coulomb. Part B, two vertical metal plates in a vacuum have a separation of 4.0 centimeters. A potential difference of 2.0 times 10 power 2 volts is applied between the plates. Figure 5.1 shows a side view of this arrangement. So this is a side view that is viewed from the sides. Smoke particle weight 3.9 times 10 power negative 15 charge, which is given by that. And this one is positive 2 times 10 power 2 volts. The smoke particle is in the uniform electric field between the plates. The particle has weight, which you have seen as that, and that charge. Show that the force acting on the particle is 4.0 times 10 power negative 15 newtons. Okay, so that is the first part of the question. We want to show that the force is that. So we know that electric field strength is defined as the force acting on a unit positive charge. And also electric field strength is PD divided by the separation of the plates, which therefore implies that the force is going to be equal to V times Q divided by D, which implies that this will be 2.0 times 10 power 2, then times that was the PD, because this is at earth potential, this is at zero potential, this is at positive 2.0 times 10 power 2 volts. And then the charge is 8.0 times 10 power negative 19. Then we divide this by the separation of the plates, which has been given as 4 centimeters. So this will be 4.0 times 10 power negative 2. We press our calculator just to verify. So this is giving me exactly the answer which has been given there, 4.0 times 10 power negative 15 newtons. On the figure 5.1, draw labeled labeled arrows, they should be labeled to show the direction of the two forces acting on the smoke particle. So 1, the particle has a mass, it has a weight, and the weight acts vertically downwards, so this is the weight. And 2, the particle is negatively charged. It is experiencing a force due to the electric field. And a negatively charged particle experiences a force in the opposite direction to the field. Note that because this is at high potential, the other is at low potential, the electric field is in that direction. A negatively charged particle experiences a force in the opposite direction to the electric field. So this is going to be our electric force. So that would be the electric force. So those are the two arrows which the examiner was looking for. Part 3, the resultant force acting on the particle is F. Determine F. The resultant force acting on the particle is F. Note that there is a weight and there's also the force to the electric field. All these ones are known. So we have the weight was, the electric force is 4.0. So this was 4.0 times 10 power negative 15. And the weight was 3.9 times 10 power negative 15. So these are vectors. The resultant of these vectors at 90 degrees is by the Pythagoras theorem. So the resultant force here is going to be the square root of open brackets, 4.0 times 10 power negative 15 squared plus, open another bracket, 3.9 times 10 power negative 15 squared. And when you press the calculator, so from pressing my calculator, I arrived at 5.6 times 10 power negative 15. You can verify with your calculator. Then the angle of F to the horizontal. So if this is the resultant force F, we want the angle it makes to the horizontal. So this is opposite adjacent, that is tan. So the angle, if I call it theta, is going to be the tan inverse. The tan inverse of the adjacent, because theta is the angle of F to the horizontal. So this is going to be the tan inverse. So this will be in the horizontal. This is the opposite, which is the vertical, that is 3.9 times 10 power negative 15 divided by the adjacent, which is in the horizontal, 4.0 times 10 power negative 15. And when I press my calculator, 3.9 over 4 tan inverse. So my tan inverse is giving me 44 degrees. You can verify. Part C. The electric field in B is switched on at a time t equals to 0. When the particle is at a horizontal displacement s equals to 2 centimeters from the left hand plate. At t equals to 0, the horizontal velocity of the particle is 0. So at t equals to 0, the horizontal velocity of the particle is 0. But remember, the displacement is 2.0 at t equals to 0. The particle is then moved by the electric field until it hits a plate. It hits a plate at time t equals to t. So it is going to hit the plate at time t equals to t. So it means the displacement s must be reducing from 0. The particle is then moved by the electric field until it hits the plate at t equals to t. So it hits the plate somewhere here. Our graph will stop there. It will start from here because at t equals to 0, the displacement was 2 centimeters. But then, what is happening for this particle? What is happening? It has its weight vertically downwards, which is constant. It has a force due to the electric field, which is constant in the horizontal, and there is a resultant force here. So since there is a resultant force, there is a resultant acceleration. Therefore, the velocity must be increasing because there is an acceleration. And how do we show that? How do we show on a displacement time graph that the velocity is increasing? Initially, it started from rest. They are saying at t equals to 0, the particle has velocity 0. So it means initially we shall have a horizontal line. Just initially it is horizontal, because the horizontal line for a displacement time graph shows that the velocity is 0 because the gradient of such a line is 0. So now we draw increasing velocity. So our graph should be becoming steeper as we tend towards t. I don't know if I have drawn it better, but let me try to modify it maybe. So it starts horizontally because initially velocity is 0, but then it is becoming steeper as you tend towards t, so that it indicates that the velocity is, maybe that one is better. So that it indicates that the velocity is increasing. So you should draw a very smooth curve which is becoming vertical. We could not draw a curve which is actually like this. The reason as why I couldn't draw it like this one means the gradient is decreasing. And the decreasing gradient means the velocity was actually decreasing, yet it is instead increasing. So a decreasing gradient of a displacement time graph will show that the velocity was decreasing because the line would be becoming horizontal. So that would be extremely wrong. So the correct graph would look like that. It is a downward slope, and the magnitude of the gradient of the line increases with time, and the line ends at exactly t against t and 0, point t ends and 0. So that would be your graph. Okay, next. Two parallel metal plates in a vacuum are separated by a distance of 15 millimeters. Distance 15 millimeters as shown in the figure 6.1. So this is the figure we are talking about. And a uniform electric field is produced between the plates by applying a PD between them. A particle of mass 1.7 exponent negative 27 and a charge 1.6 exponent negative 16 is initially at rest. That means initial velocity is 0 at point A on one plate. The particle is moved by the electric field to point B on the other plate. The particle reaches point B with kinetic energy 2.4 times 10 power negative 16 joules. Calculate the speed of the particle at point B. Calculate the speed of the particle at point B. Calculate the speed of the particle at point B. So we are going to consider the particle at point B. It is moving from point A to point B. So let's find the speed. So they have given us that the particle reaches point B with that kinetic energy. So from that kinetic energy, I can calculate the speed. Kinetic energy is equal to a half mv squared, and therefore 2.4. Sorry about this. So 2.4 times 10 power negative 16 should be equal to a half times the mass of the particle, which is 1.7 times 10 power negative 27, then times v squared. When I press my calculator to make v squared the subject, so I am obtaining 5.3 times 10 power 5 meters per second. Part 2, state the work done by the electric field to move the particle from A to B. Of course, work done is going to be the gain in kinetic energy. Work done is equal to the gain in kinetic energy, which is simply going to be 2.4 times 10 power negative 16 because the kinetic energy is that. Use your answer in Roman 2 to determine the force on the particle. Also remember, work done to move from A to B could be given as force times distance in the direction of the force. So since the work done has been given as 2.4 times 10 power negative 16, then this would be equal to the force times the distance moved, which is the separation of the plates, that is 15 millimeters. So I will simply say times 15 times 10 power negative 3. And when I press my calculator, I'm just dividing. So when I divide, the force will be 1.6 times 10 power negative 14 newtons. Part 4, determine the potential difference between the plates. Determine the potential difference between the plates. There are several ways of arriving at the PD since we can check what is given here. We have mass, we have charge. We can use E equals to V over D. there are several ways of arriving at this, but let's just go slow and say, okay, so electric field strength E can be V over D, which can also be F over charge. I think this is the most direct one. So making V the subject, V will be equal to the force times D divided by the charge. When we substitute, we shall have the force is 1.6 times 10 power negative 14 times D is 15 times 10 power negative 3 divided by Q. Q is 1.6 times 10 power negative 19. That is the charge on the particle. And when I press my calculator, so this is giving me 1500 volts. You realize that force times distance is still work done. So I would have got the PD from simply saying work done over charge. So that will give me the PD as 1500 volts. Part 5. On the figure, sketch a graph to show the variation of kinetic energy of the particle with distance x. Kinetic energy of the particle with distance x from point A along the line AB. Numerical values are not required. So we want kinetic energy of the particle from point A along the line AB. It starts from rest at A, so it means initial speed is 0. Initial kinetic energy is going to be 0. Then it arrives at this, because this is a uniform field, the acceleration is uniform, so the speed or the velocity increases by equal amounts in equal time intervals. Since it is a uniform field, A is constant. And since A is constant, then the speed increases by equal amounts in equal time intervals. And if you have studied kinematics in AS, you will now agree with me that this will be a straight line from the origin. A straight line. Here I use a ruler to draw a straight line from the origin. So that will be the graph of kinetic energy against distance. And kinetic energy is maximum when it has covered the 15 millimeters. That is the distance between the plates. Okay. Next, two vertical metal plates are situated 2.5 centimeters apart in a vacuum. The potential difference between the plates is 250 volts as shown. An electron initially at rest close to the negative plate. So there's an electron here, and in a uniform electric field, so it is uniform, so the acceleration is constant. Calculate the magnitude of the electric field between the plates. Magnitude of the electric field between the plates. So we know that electric field strength is V over D, which is going to be equal to 350 divided by 2.5 times 10 power negative 2. When I press my calculator, I get 1.4 times 10 power 4 newtons per coulomb. Show that the force on the electron due to the electric field is given by this value here. So we know that the force in an electric field is charge times electric field strength. So this will be 1.4 times 10 power 4, that is E, times the charge. The charge it was an electron, so it is 1.6 times 10 power negative 19 coulombs. And when I press my calculator, so this is giving me 2.24 times 10 power negative 15 newtons. Part B, the electron accelerates horizontally across the space between the plates. Determine the horizontal acceleration. Since I have the force acting in the horizontal, that is the electric force, so the acceleration is going to be the force over the mass. And this is going to be 2.24 times 10 power negative 15 divided by 9.11 times 10 power negative 31. That is the mass of an electron. And when I press my calculator, I just divide. So this is giving me 2.46 times 10 power 15. 2.46 times 10 power 15. That is the acceleration. Part 2. The time to travel the horizontal distance of 2.5 centimeters between the plates. The time. So the easiest equation to use to find time, I think it is S equals to ut plus a half at squared. Note that the resultant force is in the horizontal, so the acceleration is in the horizontal this time. But it started from rest. I think it started from rest. If it did start from rest, then the initial velocity is 0. Therefore, note that it also covers a distance of 2.5 between the plates, so we shall say 2.5 times 10 power negative 2 to change it to meters is equal to a half times the acceleration, which is 2.46 times 10 power 15 times the time, which is t squared. When we press the calculator, so pressing the calculator, this gives me 4.5 times 10 power negative 9. Explain why gravitational effects on the electron need not to be taken into consideration in your calculation. Why shouldn't gravitational effects be taken into consideration in the calculation of or when we are doing this calculation? Number one, when you look at the electron, the force due to the electric field acts in the horizontal, and yet the gravitational effects act vertically downwards. So that means the gravitational force in this case is normal to the electric force. So it will not affect anything along the direction of the electric force. It has no component in the direction of the electric force. So the gravitational force is normal to the electric force. The gravitational force is normal to the electric force. Or, since the gravitational force is normal to the electric force, I am saying it has no effect in the direction of the electric force, so we may not consider it in our calculation. The electric force is horizontal, yet the gravitational force is vertical, so the gravitational force does not affect the electric force. Also, you would also realize that the force due to the electric field, which I'm calling Fe, would be much greater than the force due to the gravitational field, which I'm calling Fg. These two symbols are showing much greater, much greater. Or in writing, you would just say much greater. Fe, that is the electric force, is much greater than the gravitational force. Therefore, the effect of the gravitational force is too small and can be neglected or is negligible. Next, an electron is accelerated from point A to point B by a uniform electric field as illustrated in the figure. So we know very well that a negatively charged particle experiences a force in the opposite direction to the field. Therefore, we can by now predict that the electron is accelerating. Its speed is increasing. The distance between A and B is 12 meters. The velocity of the electron at A is 2.5 kilometers and at B is 18 megameters per second. Calculate the acceleration of the electron. We have the speeds at each point. Since it is a uniform field, then the equations of motion can apply. Specifically, I think v squared is equal to u squared plus 2as would be the best equation. And when we make A the subject, I'm just going to substitute. So A is going to be V squared. V squared, it is in kilometers per second, megameters per second. So V is 18 times 10 power 6 to change to meters. But this should be squared minus U squared, which is 2.5 times 10 power 3 to change it from kilometers to meters. Then I will divide this by 2s, where s is 12 meters, so that will be 2 times 12 times 10 power negative 3. And when I press my calculator, so when I press the calculator, the acceleration I obtain here is 1.35 times 10 power 16 meters per second squared. The change in kinetic energy, since kinetic energy is equal to a half, mv squared, or I will simply say the change in kinetic energy at one point it will be a half m. So final velocity v squared minus initial velocity u squared, that will give me the change in kinetic energy. When I substitute, this will be a half times the mass. The particle is an electron. The mass is 9.11 times 10 power negative 31. Velocities, we have 18 times 10 power 6, and this is squared, minus. The other one is 2.5 times 10 power 3, and this is also squared. So that is our change in the values of V, but they are squared. Do not write, it is wrong to say that change in kinetic energy is equal to a half m into V minus U squared. This is wrong mathematics. Do not be tempted to do such mathematics. So the change in kinetic energy, when I press my calculator, so the change in kinetic energy is 1.48 times 10 power negative 16, which is approximately 1.5 times 10 power negative 16. That is the change in kinetic energy. Okay, next, the electric field strength is what we want now to find. That is E. So by definition, electric field strength is the force per unit charge. So this will be the force over the charge, which is the charge of an electron. Or since we have acceleration, we can say it is the mass times acceleration over the charge. And when we substitute, this can be 9.11 times 10 power negative 31 times 1.35 times 10 power 16 divided by 1.6 times 10 power negative 19. And when I press my calculator, Okay, so my calculator had jumped, but it is giving me a 7.7 times 10 power 4. 7.7 times 10 power 4. Okay, next, an alpha particle moves also from A to B in the electric field that we have just seen. Describe and explain how the change in the kinetic energy of the alpha particle compares with that of the electron. Numerical values are not required. Numerical values are not required. So where we had an electron, we are now having an alpha particle. What do we know about an alpha particle? If the electron is moving in the direction A to B, if the electron experiences the force in the direction A to B because it is negatively charged, the alpha particle experiences a force in the opposite direction. That's number one. Number two, look at the charges. The charge of an electron is E, and the charge of an alpha particle is actually twice E. And yet this force is given by charge times electric field strength. The same field, it means the alpha particle experiences a greater force. In fact, it will experience a force which is twice that of an electron because of the charge. So the two major important differences are as a result of the charge. One, the alpha particle and the electron have opposite charges, so they experience forces in opposite directions. Two, the magnitude of charge of an alpha particle is twice the charge of an electron. Therefore, the force experienced by the alpha particle is twice in the magnitude that experienced by the electron. So just for completeness, we can fill this part here and say that the charge on an alpha particle, the charge on an alpha particle is opposite to the electron charge. The charge on an alpha particle is opposite to the electron charge. The charge on an alpha particle is opposite to the electron charge. Therefore, because the question is describe and explain how the change in kinetic energy of the alpha particle compares with that of the electron. So it means the change in kinetic energy, or let's say if we put an alpha particle in that position and moving it towards B, we are moving it actually in the opposite direction to the field. Although it experiences a greater force, note that it is in the opposite direction to the field, and yet a positively charged particle is supposed to move in the same direction as the field for it to speed up. So this time the kinetic energy is going to reduce. Kinetic energy is reduced. Or we can say the change in kinetic energy is going to be negative. Moving an alpha particle from A to B, if we move an alpha particle from A to B, we are moving it against the field, yet a positive charge experiences a force in this direction. So moving it against the field, it loses kinetic energy. So it slows down, the kinetic energy is reduced. And also the charge of an alpha particle is greater. In fact, it is twice. In fact, it is twice that of an electron. The charge of an alpha particle is greater or twice that of an electron, and this causes the change in kinetic energy, or causing twice a change in magnitude of the kinetic energy. So this causes twice the change in the magnitude of the kinetic energy. Okay, next. I don't want this video to be very long, so I'll stop on a few pages. Let's just conclude with a few more. So the next will be in the next video. So here we have an electron traveling in a straight line through a vacuum with a constant speed. The speed is constant in a vacuum. Then it enters a uniform electric field, AB. The electron continues to move in the same direction until it is brought to rest. It comes to rest. Why does it come to rest? Perhaps it was moving in the opposite direction to the force acting on it. That's why it is coming to rest. It was moving in the opposite direction acting on it. And when a body moves in the opposite direction to the acceleration, it slows down until it comes to rest. So the question is, state the direction of the electric field. So because it comes to rest, it was moving in the opposite direction. It was moving in the opposite direction. The force on it is in this direction. Remember, the force on a negatively charged particle is in the opposite direction to the field. That means this side is most likely going to be a positive plate and the other side is most likely going to be a negative plate because it is slowing down. So the force on it must be in the opposite direction to its motion. And the force on a negatively charged particle in an electric field is towards high potential. So we can predict that on the left the plate is positive and on the right the plate is negative. So the question is, state the direction of the electric field. So the field lines originate from high potential to low potential. Therefore, it implies that the field lines are originating from the left and they are terminating to the right in that direction. So the question is, state the direction. So I can say in the same direction of motion as the electron, or I can say to the right. I can say to the right. I can also say from A to B in that direction, or I can say from the left. So the electric field is from left to right, left to the right, left to right. I hope people will have picked why we are saying the electric field is from left to right. Number one, the electron is slowing down, it is coming to rest. The reason as to why it is coming to rest, it is maybe because it was moving against the force acting on it. And if the force, it was moving against the force acting on it, then we can say the force was acting to the left. Note that the force on an electron in a uniform electric field acts in the direction of high potential. So that means the force, where the force is pointing is where we have high potential or where we have a positive plate. That's why I'm saying the plate on the left is at high potential and the plate on the right is at lower potential. But again, remember, field lines originate from high potential to low potential. Therefore, the electric field is from the right to the left. Calculate the magnitude of the acceleration of the electron. Calculate the magnitude of the acceleration of the electron. Magnitude of acceleration, of the deceleration of the electron. So here we shall simply use v squared equals to u squared plus 2as. And we want the acceleration, deceleration. Acceleration is a negative, deceleration is a negative acceleration. I'll just substitute. Acceleration is going to be v squared. V is 1.5 times 10 power 7. And this is squared minus u. Remember, it started from rest, so that was minus 0. Divide by 2 times the distance it has moved from A to B, which is 2.0 times 10 power negative 2. 2.0 times 10 power negative 2. Oh, sorry. The other way around. The speed is the other way around. So it will be 0 minus because it will end up being a negative. So this is supposed to be 0 squared minus 1.5 times 10 power 7. And this is also squared. Of course, this will give you a negative, but the negative just implies a deceleration. So when I press my calculator, when I press the calculator, I have that the deceleration is actually 5.6 times 10 power 15 meters per second squared. Part C, calculate the electric field strength. Calculate the electric field strength. So to calculate the electric field strength, we know that E is defined as the force acting on a unit positive charge. So this will be, of course, the force is mass times acceleration over charge, and the mass is 9.11 times 10 power negative 31. The acceleration is the deceleration, which is 5.6 times 10 power 15 divided by the charge is 1.6 times 10 power negative 19. When I press my calculator here, so pressing my calculator gives me 3.2 times 10 power 4. That is the electric field strength. Of course, I've ignored the negative because it just shows a deceleration. It just shows that the particle is moving in the opposite direction to the field. Part D, the electron is at point A. The electron is at point A at t equals to 0. Note at point A it has a high speed. And they're telling us to sketch the variation with the time t of the velocity v of the electron until it reaches point B. Numerical values are not required. Note that at point B velocity is 0, at point A it has 1.5, at B it is 0. So it means since it is a uniform field, the velocity decreases uniformly. Therefore, this is going to be a straight line. This is going to be a straight line, so you put there your ruler and draw a straight line. So that is going to be the graph. It is a straight line going to 0. The electron is slowed down and it comes to rest at point B. So this is point B where the velocity becomes 0. Okay. A potential difference of 2.5 kilovolts is applied across a pair of horizontal metal plates in a vacuum as shown below. Each plate has a length of 5.9 centimeters. The separation of the plates is 4.0 centimeters. The arrangement produces a uniform electric field between the plates. Assume the field does not extend beyond the edges. That means after the edges, it is maybe a vacuum. An electron enters the field at point A with a horizontal velocity 3.7 times 10 power 7 meters per second. Along a line midway between the plates, the electron leaves the field at point B. Part 1. Calculate the time taken for the electron to move from A to B. That is the time between the plates. I think that is easy. From S equals to ut plus a half at squared. Note that the field is vertical because the positive plate is up, the bottom plate is negative. The field is vertical downwards. There is no acceleration in the horizontal, so this part becomes 0. Then the length S is going to be 5.9 times 10 power negative 2. Initial velocity, the velocity with which it enters is 3.7 times 10 power 7, then times t. So I make t the subject and I just divide. So when I divide, I get 1.6 times 10 power negative 19 seconds as the time there. Calculate the magnitude of the electric field strength. E is defined as, or it will be V over D. They've given us the PD between the plates as 2.5. The separation of the plates is this plus that, which is 4 centimeters. So I'll simply substitute 2500 divided by 4.0 times 10 power negative 2. And when I press my calculator here, so this is giving me 62500. In other words, that is around 6.3 times 10 power 4 newtons per coulomb. Show that the acceleration of the electron in the field is 1.1 times 10 power 16. Show that the acceleration of the electron in the field is that. So we know that force is mass times acceleration, or we know that E is equal to F over charge, which is the same as mass times acceleration over charge. Therefore, we can simply say that the acceleration is going to be equal to charge times E divided by the mass. And when we substitute, we shall have 6. The field strength is 6.3. The charge it is an electron, 1.9 times 10 power negative 19 times, I'll write 62500, the more exact value, divided by the mass of an electron, which is 9.11 times 10 power negative 31. I'm pressing the calculator to check. So when I press my calculator, this gives me 1.1 times 10 power 16 to two significant figures, meters per second squared. Use the acceleration given in part 3 and your answer in part 1 to determine the vertical distance. In part 1 we have time. In part 3 we have acceleration. So I'll use equations of motion. S is equal to ut plus a half at squared. S is ut plus a half at squared. Note that the electron started from rest, so initial velocity can be considered to be 0. Not really. Initially in the vertical, velocity is 0. So if I consider vertical motion, S is going to be equal to a half. Acceleration in the vertical is 1.1. 1.1 times 10 power 16, then times t, which is 1.6 times 10 power negative 9, and this is squared. When I press my calculator, this will be 1.4 times 10 power negative 2. 1.4 times 10 power negative 2. So that is the vertical displacement, but that they want y. The distance we have just calculated, if I was to draw a horizontal line along here, the distance we have just calculated is this one here, so that is the S, but we want y. S plus y is 2 centimeters because this S plus y is the distance from the horizon, from this point to that point. So if I want to find y, then I will subtract. Therefore, y is going to be 2.0 centimeters minus S. My value of S in centimeters, I think it is 1.4 centimeters. When I press my calculator, this one doesn't need a calculator, that is 0.6 in centimeters. Explain why the calculation in 4 does not need to include the gravitational effects of the electron. Explain why the calculation in part 4 does not need to include the gravitational effects on the electron. Now here I can't say that the gravitational force is normal to the electric field, not at all, because when you look at the diagram, the weight is downwards and the field is also downwards, so that one cannot work. But I can still say that the force due to the electric field, the electric force, The electric force is much greater than the gravitational force on the electron. The electric force is much greater than the gravitational force on the electron, or the force due to the electric field is much greater than the force due to the gravitational field, or the acceleration. Somebody will say acceleration due to the electric field is much greater than the acceleration due to the gravitational field. Okay. Lastly, I want us to stop on this part here. The electron enters the field at time t equals to 0. On the figure, sketch graphs to show the variation with time t, the horizontal component Vx of the electron. So since the field is vertical, it means there is no resultant force in the horizontal. What does that mean? The speed in the horizontal does not change because there is no acceleration in the horizontal. So that means it will be a horizontal line. Then part 2, the vertical component Vy of the velocity of the electron, a vertical component. Because the field is uniform, the acceleration in the vertical is uniform. Therefore, the speed increases by equal amounts in equal time intervals. Remember, initial velocity in the vertical was 0 because initially the electron entered horizontally. So it means we shall have a vertical straight line. We shall have a straight line which starts from the origin. So we shall have here a straight line starting from the origin for the vertical component. Because for the vertical component, v in the vertical is equal to initial velocity in the vertical, which is 0, plus acceleration in the vertical times t. So there is an acceleration in the vertical which is uniform, so the speed increases in the vertical by equal amounts in equal time intervals. That means that would be a straight line. I want us to stop at this point. We shall start from here. I hope you have had a very good experience with this, and we shall meet in part 2. See you in part 2. Thank you.